Okay, our next lesson is on gravitational field strength, and it's very similar to what we just did with Newton's gravity formula, but the only difference is what happens if we have only one object. So Newton's idea was if we have two masses, there is going to be gravity acting between the two, but the idea is, well, if mass 2 gets pulled towards mass 1 because it's smaller, what's happening? What's causing that? So Newton and others came up with ideas that, well, let's call it a field. So what happens is it's sort of like an imaginary attraction. So if we only have one mass, there is actually going to be gravity. It has a gravitational strength that's going to pull objects towards the center of it. So we'd have a gravitational field that acts in every direction on this object, pulling it towards it. So if we're standing on the Earth, we're getting pulled towards the Earth due to the gravitational field of the Earth. So the question is, how do we calculate that, and what would that represent? So what we do is we say, well, if we're standing on the Earth, we know the force of gravity is just mass times gravity, because that works for just the force of the Earth. But we also know from Newton's gravitational formula, we have G m1 m2 over r squared. But if we're dealing with an object on the Earth, we could actually make these two equal to each other, because it's the same force of gravity if it's dealing with the Earth. So if we put the two formulas together, we would get mg equals gm1 m2 over r squared. And in this case, the little mg is the mass of the person or whatever that's on the Earth. And then in the big formula, we have the mass of the Earth times the mass of the person. So actually, these two masses we could cancel out because we're dealing with the mass of the person or whatever the other object is on the Earth. So what we do is when we do that, we get a new formula, and it's little g equals gm1, or just g times the mass, divided by r squared. So in this case, the mass that we're talking about is the mass of the planet, the Earth, or whatever it is, that has the gravitational field strength. The g number is still the same, and our distance is obviously whatever distance you are away from the center of that object. So if we plug this into our formula for Earth, so if we put in 6.67 to the negative 11, we do our 5.97 to the 24 for mass of the Earth, and we put in 6.27 to the 6 for our radius of the Earth, and we actually plug that into the formula, we get an answer of 9.81, which we already know is the acceleration of gravity of the Earth. So that's where the 9.81 was calculated from, is using this formula. The only difference is when we're talking about the acceleration of gravity, we would write it as meters per second squared. But in this case, if we're talking about gravitational field strength, really what we're usually dealing with is a force divided by a mass. So quite often it'll also be written as a Newton per kilogram. Okay, so either of those two units mean the exact same thing. So what happens is then this new formula we can actually use now to calculate any acceleration of gravity or gravitational field strength of any object of any size. So if we were to pick, let's suppose we have some unknown mass that weighs 5,000 kilograms, and we were standing, let's say we are 0.25 meters away from it, away from the center of it, so center to center, 0.25 meters, we could actually figure out what the acceleration of gravity is at that point due to that object. So all we would do is we plug in our 6.67, times it by the mass, so 5,000, and divided by 0.25 squared. If we plug that in our calculator, that'll tell us what the acceleration of gravity is at that point, 0.25 meters away. And once again, because our mass is fairly small, we're probably going to get a really small number for gravity. And we do. We get 5.33 times 10 to the negative 6. Okay, so obviously that number is way too small that we wouldn't do anything. So if we were standing close to a 5,000 kilogram rock, nothing's going to happen. It's too small of a gravity for us to notice it. And the other thing, if this was on the Earth, we're standing next to a big rock, we also wouldn't notice it because the gravity of the Earth is way stronger, so we're feeling ourselves getting pulled downwards. We're not going to get pulled sideways. So the only way you'd actually be able to feel the gravity of another object would be if it was right above you. So Earth was pulling you down, you had some other object pulling you up, you might be able to sense the change in the gravitational pull that would cause that. But for that to happen where you'd actually feel it, we'd need a massive object, like it would have to be near the size of the Earth or something like that for you to actually notice the difference. So if we change this question to, instead of being 5,000 kilograms, we change it to 5,000 or 500,000 or 5 million or 5 billion or whatever, then obviously the bigger that number is, the bigger the gravity is going to be. But just like the other formula, you can use this one the same way in order to calculate the gravitational field of any object at any distance from it.
Okay. So yeah, that's what I did with him yesterday, and he was.
So in this case, we would get 4.18 times 10 to the negative 9 newtons, and because they're both going to the right, we could just say to the right or towards A or towards B or however. And that's it. We'll stop there.